So the determinant is not typically thought of as a linear thing, but there is one regard in which it does behave linearly, and that's with respect to columns as arguments. So as a function, the way that you normally think about it, so we usually think of det as being a function from fnn to, well, actually, sorry, that should be f, to f. It's not linear. So for example, if we take like 2 times the identity, then this guy looks like, you know, a diagonal matrix with just all 2's down the diagonal. So the determinant of 2i is going to be 2 to the n, which is not the same as 2, which is, oh, I ran out of room. 2 is the determinant of I plus the determinant of I, because the determinant of I is 1. All right, so, however, if we think of our matrix A as being a vector of vectors, so here's the first column v1 down to the last column vn. So I guess in the textbook we'd probably write this as a list of vectors in this way. So we're thinking of it as a list of vectors or an n tuple of vectors, which means that it's in fn crossed with itself n times, right? So this is isomorphic, sort of canonically, naturally isomorphic to fnn. Then this guy, so det as a function on an n variables, each one of which is an n vector, is linear in each variable. In each slot. So you can think of det as a multilinear function. Multilinear just meaning linear in all of its arguments. And this is just a direct definition, or sorry, consequence of the definition. Writing down the proof is a little bit awful, so I'm not going to do that. I'm just going to give you an example. But the statement here is that the determinant of, and so if we have a bunch of n vectors, and then we have some, I guess I don't need a coefficient on, subscript on the coefficient, but here we've got avk, so we've got avk plus buk, so there's a linear combination of things in the kth slot, and then everywhere else there's just a vector. Then we can pull this apart as a det v1 vk vn plus b det v1 oops, that's a u uk vn. Okay, so in each slot you can do this. All right, multilinear function. Okay, so let's look at an example. And so we'll take this matrix 2, 0, minus 1, and then the middle row, or middle column, I'll write as 1 plus 3, 2 minus 1, and 1 minus 1. And then third column as minus 1, 2, minus 2. Okay, so on the one hand, we have that the the determinant of, if these things are added together, 2, 0, minus 1, then those numbers are 4, 1, 0, negative 1, 2, minus 2. So let's see. So this is going to give us minus 4 and minus 8 and a plus 0 and then a minus 1 and a minus 0 and a minus 0, which will be grand total negative 13. Then I can also do this piece by piece. So if I do 2, 0, minus 1, 1, 2, 1, minus 1, 2, minus 2. So that's the first part. And then I'll also work out the one where I take the second column vector down the middle. So that's 3, minus 1, minus 1. So from the first one, I'll get minus 8, minus 2, 0, and then for my negative terms, I'll have minus 2, minus 4, minus 0, and so that gives me minus 16. And from the other one, I get 4 and minus 6 and 0, and then from the negative ones, I'm going to get minus negative 1, minus negative 4, and minus 0. And so adding those together, I get 3. And sure enough, minus 13 is minus 16 plus 3. So the reason, or the way to see why this works out, is if we look at the terms that I have that are giving me this one in the middle. Let's see. So the minus 4 comes from 2, 2 minus 1, and minus 2. And then the minus 8 comes from 1 plus 3 times 2 times minus 1. And then the 0 comes from minus 1, 0, 1 minus 1. And you see what's happening is that every term from the determinant is going to have exactly one item from column 2. So it's going to have one of these factored ones. And then wherever there's this factored one, it can be split apart into 2 terms. So 1 times the other stuff and 3 times the other stuff. 1 times the other stuff and minus 1 times the other stuff, etc. And those can be gathered into the corresponding determinant terms. And I guess I should, by rights, I should also include the negative ones here. So what do we have? So we've got minus 1, 2 minus 1, 1 minus, sorry, that was just minus 1. And then minus 1 minus 1, 2, 2, and then minus negative 2, 0, 1 plus 3. So again, each of those ones where it's written as a difference, you can distribute that term and split it into 2 pieces. And the first one goes here, and the second one goes here, and that's why it works. And then you can also see for scalar multiples, it does basically the same thing.